Hello and welcome to quantum computing meetup. I'm going to be talking about solving differential equations with Quandela quantum processors. My name is Andrew Miller and I am a software engineer with about 10 years of experience. I love quantum computing and I call myself a quantum computing enthusiast. And I like to try various quantum computing frameworks. So the ones that I tried are IBM Qiskit, D-Wave Ocean, and now I'm going to be trying Quandela Percival. But I've also heard of other frameworks like Ticket and more recently Penny Lane, and I'd like to continue trying those and make more videos and presentations showing how those could be used. And this presentation is going to be twofold. First, I'm going to show some slides just to give some background on the topics of differential equations and photonics quantum computers. And then I'm going to jump into Jupyter Notebooks and basically go through a demo of how you would solve this problem on a quantum photonic computer. So let me get into this, and I'll start by talking about differential equations. So differential equations are basically equations that operate on derivatives of a function. Function would be some sort of an operation that you perform, and derivative represents rate of change of that function. So the common examples where this comes in are in physics and engineering, where you seek to predict motion of objects, of fluids, or obviously also quantum particles in quantum physics. Also, another example that probably might resonate is in economics and finance, where you're dealing with equations that analyze gross domestic product. You might also need to compute derivatives there. And the main promise that I personally see from quantum computers in the space of differential equations is the speed. When we enter the age of quantum advantage, we expect significant speed gains by employing quantum computers to solve these problems. Now I wanted to show what a differential equation looks like and what solutions might look like. So here on this figure you see that there's this equation y prime equals 2x, and in essence y prime is a derivative, and this equation actually has multiple solutions, and they're all plotted on this diagram here, and the reason why it has multiple solutions is because you can take multiple functions that are different by a constant, in this example here c, and you can compute their derivative and this equation will still be satisfied. And so in differential equations, a lot of times we need a specific solution, not a family of solutions, especially if you're doing numeric methods of solving. So you can solve these equations analytically, which is basically like is shown here, where you have the actual equation, or you can solve it numerically, where you tabulate the data set, basically build a grid and solve the equation at grid points. So in this case you can see that we're looking for a specific solution, and the solution we're looking for is the one that passes through this point to 7, and if you substitute the values, you find out that such solution is when C is equal to 3, and this point is what's called a boundary condition. So this is one of the ways that you can specify which specific function out of the family of functions that you need as a result. All right, so next I want to talk about what a photonic quantum computer is. Now, in essence, a photonic quantum computer uses photons to represent qubits, and is typically comprised out of several components. Namely, they are optical fibers which transmit the signals. You also have scattering units that basically direct photons, and then you have ring resonators that can do multiple things: entangle photons or store them, so you can use them as this idea of memory. Then you also have, which is I think the most probably important part, is photon detectors, because you need to, in order to convert quantum information back into classical information to bits, you have to have photon detectors, and of course without photons themselves you can't the computer wouldn't work, so you also need a photon source. And another important component is electro-optic modulator, and those typically control things like power, phase, or polarization. And a good example of that would be Mach-Zehnder interferometers, but you can also technically have things like beam splitters or phase shifters, and that will come in next. Okay, so so the typical view that you can find online, and this specific image that I have on the screen is from an article in the Nature magazine, and it shows sort of my understanding is this is sort of this generalized idea of what a photonic quantum computer looks like. And so you see here they have on the left, top and bottom, there's a couple of sources of photons. Then you have EOMs, electro-optic modulators, on the bottom there, in the middle, and on the top in the middle you have resonator coupled quantum memory, which is, like I mentioned, a lot of times you will see that it's a scattering or ring scattering component, or scattering ring, depending on how you say it. But next slide will actually show there's multiple implementations for all those different components. And at the very end you have two things, the photon detectors, and you have classical controls, because at some point you have to convert the qubits back to classical bits. Although I think one of the biggest promises of photonic quantum computers is that eventually you might not need to convert to classical computers if you can have, because we already have quantum photonic communications, right? We use optic fibers. So what that means is you can have your communications done with photons, and then that naturally flows into photonic computers. And let's see, so I want to show this is sort of the table from the same article in Nature. It talks about the different ways that you can implement this components, and so you can see that for a quantum emitter you could use quantum dots, but you can also use trapped ions and nanotubes, and the same for many other ones. And so I'm not going to go through the whole table, but this is just to give you an idea. And here also the EOMs, where you can have Mach-Zehnder or beam splitters and so on. Think of it as like elemental base in a classical computer. You know, you have different types of transistors and diodes and capacitors. This is sort of the same. It's in the photonic world, right? That's what you get. All right. So I'm going to try to abstract a little bit away from the hardware and try to be more genetic, like more abstract. And when you start building circuits, because if you look at the previous diagram, right, this actually is a circuit. But when you need to write a quantum program, in essence, you have to, at the low level, right, it's building a circuit. And well, it's really finding a way to map your logical circuit into the real circuit. And so here, the basic building blocks that are used, and specifically in Acela and in Percival, are permutations, phase shifters, beam splitters, and then you can compose Mach-Zehnder interferometers out of them to get some more complex operations done. And these quantum computers, they unlike the sort of the superconducting qubits, where you actually measure how many qubits you have in the system. In a photonic quantum computer, you use two terms, primarily photons, the number of photons the system has, and the number of modes. And modes are basically different degrees of freedom that a photon can have. And examples will be like frequency, polarization, position, and they're modeled as Fock states. So this is a view of a Acela quantum processor, and it has 12 modes and up to 6 photons. And it's a universal quantum computer, so it basically can do the same things that like IBM quantum computers can do, or any other universal quantum computer can do. One of the things that I noticed is that availability was limited when trying to use this hardware, so I mostly was using simulators to experiment with the system. And so this is where I get to Percival. So like I mentioned, similar to how IBM Quantum has Qiskit, and you have D-Wave has their Ocean software, and you also have Ticket, which is, I believe, IonQ, and Xanadu has their Penny Lane. Quandela developed their own framework called Percival for manipulating the circuits and solving problems on a quantum computer. The one note that I have, though, about this framework is that it is a low-level API only. And so you have to figure out how to, in essence, build your circuit or train your circuit yourself. The way that I think of it as a software engineer is it's more like assembly language versus a high-level programming language. So like think of it as almost like you're writing in machine code versus you're writing code in something like Python. In reality, of course, Percival is all based on Python, but what I'm trying to get to is that you have to use low-level primitives to interact with the system, so like circuit primitives. There's no high-level language that say, hey, I want to do a quantum Fourier transfer, or I want to run Shor's algorithm, or VQE, or any other number of either purely quantum or hybrid classic quantum algorithms, like you could in systems like Qiskit or D-Wave Ocean. All right, so now is the time for demo. So I'm gonna shift to the notebook and demonstrate what that looks like. So here I already logged into Quandela Cloud. It's free, and they give you credits initially, so you can see I got some credits both on the real hardware but also on the simulator. They give you, I believe, about 10 hours on simulators and about 1 hour on real hardware. So here in the platforms tab, you will be able to see availability of the various platforms. over either the last week or the last month. And I'm just going to show the last month. So here on the right, you can see this QPU, a Cella, which is the actual hardware, the real photonic computer. But you also have simulators, Clifford, SLOS, and Cella simulators. And if you look at the availability, so the blue line is a Cella. It's the one that's kind of like, it's not at 100%. It's kind of here in the middle. And I am not sure what like 60% availability means. To me, as a software engineer, it could mean that it was available a few hours in a day, but I think it might be interpreted as perhaps there's not one QPU but many, and some of them were available. So it's hard to say, but here it says available time per day. So I think it's really how much uptime the system had. And you can see some days there was absolutely no availability. So I did get a sense that the system is still highly experimental, and they're still working on making it more robust and stable, where it's, you know, anywhere close to 100% uptime, which is of course really expensive to have that, but at least something close to at least 90%. All right, so this is the jobs tab, where it shows you the different runs that I made, and some of them completed successfully, some of them failed. And I actually ran one of the, so I took an example from their website, and in essence I tried to run it on simulator and on the real quantum computer. And what was interesting was the same program that ran fine on the simulator for a Cella, it failed on real quantum hardware, which was surprising to me. I didn't expect that. I thought that it would actually work. It didn't make a lot of sense, so I'm not entirely sure why or how. It might be that I'm doing something wrong, most likely, but at the same time, like when I used, you know, frameworks like D-Wave Ocean and running on real hardware in my previous presentation, I had no problem running it on real hardware, in the sense that, you know, it would run. There might be results might be, you know, different, but that's a whole other topic. Same with Qiskit. Most of the time, the only times where I had problem was, you know, let's say the problem was too big and the transpiler didn't know how to map it properly to a smaller device. But that's like, it actually, the error messaging was fairly clear. It told me what was happening, versus here, when I looked at the error message, it didn't make a lot of sense, and actually the interface is kind of difficult to get to the error. But it just says list assignment index out of range, which, even though I'm a software engineer, it could mean many things. And so again, very difficult to follow the error messaging. I gotta give their support credit though. When I was originally signing up for the platform, I wasn't able to log in, even though when I got the welcome email. But I contacted support, and the next day everything was fixed and I was able to get in. And then the second time I was trying to get in, I also had trouble trying to adopt the examples that they had for differential equations to run on real hardware, and their support was actually very helpful. However, they didn't fully sort of solve the issue for me. They gave me some clues, but I don't have enough information to follow those clues, and I will talk about that in a moment. So anyway, let me get into the notebook. So here I'm going to be opening the tutorial first, because I wanted to talk about the linear optical components and the framework as well. And so here, Percival, you can import it as a library in Python, and you can express various states either as a string like this, basically a qubit, or you can express it as an array. and those are Fock states, and you could manipulate them. And when you run on real hardware, that's also the output of the machine. It gives you the frequencies for different states that came out, that were detected. I want to talk about linear optical components because this is where it's very interesting, because one of the things that Quandela claims on their website is that photonic quantum computers have an advantage. They can do things that like superconducting qubits cannot do. At least that's the way that I understood the messaging, which is very interesting. It could be an advantage of their hardware. But if I had to compare, one of the things that is as far as I understand is not possible is copying a qubit, right? You can't copy it. You have to what's called do a swap or permutation. And if you use like Qiskit, they call it swaps. So you can swap, and basically it allows you to take a qubit and route it to another part of your circuit, such that then you could take advantage of the data and amplify the solutions that are important to you. And in general, right, when you're trying to solve problems on quantum computers, you seek to amplify the solutions that are important and de-emphasize, so to speak, the solutions that are irrelevant or actually harmful. And so this is permutation. Other systems call them swap. Then you also have a phase shifter, and phase shifter has a parameter, so you can parameterize it, basically the phase you want to do the shift with. Then you also have a beam splitter, and beam splitters, so you can do many things with them. Like an example of a beam splitter, you can entangle qubits, or photons really, like Hadamard gate. This is an example. And you can also do controlled rotation gates. And as far as I understand, you basically combination of these three operations, you can build any universal quantum computing gate that you need. And one thing that I noticed though is the beam splitter. I was expecting this gate to show up in the center, because like, how is it beam splitting if it's here, right? There's only one fiber or pathway for the photon to go. It didn't make a lot of sense to me. And the idea, right, is that when you split the beam, the photon can go either right here on this diagram to pathway 0 or pathway 1, or if you look at Quandela, right, modes to mode 0 or mode 1. But logically how they denote it didn't make a lot of sense. I must not understand it fully, the notation and why that is, but that's one thing that kind of got me confused. And what you can do is, so you can manipulate phase shifter, but beam splitters also are basically configurable. And so you can also, and this examples are just something like pre-canned beam splitters, but in essence they have parameters as well. And so you can, if you're doing quantum machine learning, right, you could train the parameters for phase shifters and beam splitters in a way that will give you, in essence, will amplify the right solutions and de-emphasize the ones that you don't need. All right, so let's see. So another thing that is interesting to note is when you build circuits, so they show you how you can build circuits with this thing. There's two different syntaxes. One is you use the add command or method or function, and you pass in the mode that is the input for that specific part of the circuit, and then the actual circuit. And so you can then stack them, so you can like compose things out of them. And so this here they're basically saying, well, this phase shifter PS comes first, and trying to actually visualize it. Let's see. So the circuit right here, yes. So, and I think that it sounds like it's in reverse order from everything that I'm seeing, and so right here, beam splitter on node 1. So this is the beam splitter on node 1, and then it's preceded by two phase shifters. So right here, or not? Yeah, it's followed by two phase shifters, and so this one and this one, and so it's kind of backwards. But the equivalent syntax is you could use double slash, and it sounds like when you do double slash, you still follow the same order as before, and you can either chain operations or just have them on separate lines. Yeah. So and in fact, yes. So actually, now that I look at it, it's sorry, I was wrong. Yeah. So it's in fact, it's in the same order that you provide the parts of the circuit. So you start with the beam splitter, then you have the pi over 2 phase shifter, and this one is just phi, and at the very end you have another beam splitter from rising off of mode 1. So yeah, so this is two syntaxes that you can use to build the circuits. Let's see. So this is a more complicated example where they're building a complex circuit. So they're using this Bell state prepare circuit, which is consists of two beam splitters and a permutation. And if you actually visualize it, so you can visualize it as a sort of a black box circuit, or you can visualize it with low level, right? What are the different beam splitter and phase shifter and permutation components within it? And so here, this is what it looks like. But in essence, these two boxes here, they're MZIs, Mach-Zehnder interferometers. And if you look at the examples, when they run them, you get the output or the results dictionary. It consists of basically the state and how many hits that state had, or how many times the state was detected. And like this example, right, they ran 1,000 shots of the circuit, and this is what they got. One thing to note is they don't include the states in the results. They don't include the states that are not detected, and this actually will come in. It causes some issues with the example that I'm going to show, but bear with me. I wanted to show one more thing, which is, so going back right to sort of universal quantum computers. So you have the sort of the standard gates, the rotations, controlled rotations, Hadamard gate, and they basically give you sort of an exercise. Go ahead and build basically implement these gates using the beam splitters and phase shifters and permutations. But suffice it to say, it is possible to do that, and they have a whole Qiskit conversion notebook. As far as I understand it, basically it uses some of these principles of how do you build the universal quantum computing gates to then sort of convert code or convert circuits that you have in Percival to something that will run on Qiskit. All right. So next, I'm going to go to the differential equations notebook. And this notebook, it also comes with Percival when you first open Notebook, when you first log in and open it. However, when I logged in, the version of it was a bit out of date, and I had to manually kind of update it from their website. And that was mainly, this was an interesting thing with their backend implementation. So they have a couple of abstractions, and I'll pop out the GitHub page and just show the difference there. But let me just get into the actual differential equation notebook and kind of go through it and talk through different pieces of it. So it's based on a few papers, and they cite the papers at the end. The first paper here actually comes up with, in essence, a way to take this specific differential equation and come up with a loss function that will result in the solution for that specific equation. Of course, this is not a genetic differential equation solver, and there's different classes of differential equations, but this is just an example, just to get an idea of how you might go about using a quantum computer to solve these equations. And so the general idea here is that you use quantum machine learning. So you, in essence, you learn some sort of set of weights or matrices that contain weights, and then those weights, when you and if you talk about the photonic computer, the weights are basically your parameters for your phase shifters and your beam splitters, and so then you when you learn those, you can then compute the sort of, well, how do I put it? When you've learned them, what that means is your circuit corresponds to the loss function of that specific equation. And what that means is when you run the circuit, it will give you the solution to the to this specific equation. And of course, this solution is a numeric solution, meaning that it's you're not going to get an analytic solution, even though we know an analytic solution for it. And in this particular example, it might not actually make a lot of sense. This is probably very tractable from looking at this, very tractable in a classical computer, but there might be equations that are hard computationally to solve, or there is no analytical solution, at which point something like this might actually outperform, especially if you have a powerful enough machine. Anyway, so I don't want to get into the math because, quite frankly, I don't fully understand the math myself. But just suffice it to say that based on all the papers, this specific equation right here basically represents if you train a circuit in a way that the loss function is minimized, this specific circuit that corresponds to this equation, you in essence will have a circuit that solves that equation. And there's a lot of fancy math, but I think what helps to understand it is actually visualizing it. And so so here they express the circuit. So you have W1 and W2, and then you have a phase shifter. And so if you go back to the sort of the theory of it, so you have W2, W1, and you have the phase shifter, which is S. All right, so in essence, what the process then of getting a circuit that solves this problem is an optimization problem. And the way that this is done in this notebook is they build a function called computation, and in essence, what it's doing is computing the value of the loss function given W1 and W2 and the phase shifter. Now you start out, if you look at this example, with a random unitary matrix, basically to you feed, and then as a circuit. And then Percival has some smarts, as far as I understand it, under the hood. It knows how to map it all to like physical hardware, so at least you don't have to figure that part out. But what happens then is you can run a classical optimization algorithm. So here they picked BFGS, but it could be any number of algorithms that you can pick out of sort of the classical toolbox. And so and this runs on a classical computer. And so if you look at this code here, it basically it should be let's see, not this code but this code. So it calls minimize, which is basically there's a SciPy minimize function that allows you to run classical optimization algorithms. But what you pass in is the computation function. And the computation function is the one that's actually leveraging the hardware. So in this case, they're using backend and they're setting the circuit, and then they are doing the computation, right, by saying backend all probabilities. So that gives you, in essence, the example where I was showing the various states and the frequencies, or how many hits each state had. So I'm going to actually run this. What we'll see is that this will start converging, right? So because the algorithm, in essence, knows how to it basically manipulates the values of the parameters, which are basically this W1, W2, which are basically unitary matrices, but they represent the circuits, the logical circuits to solve this problem, and the phase shifter. And so it knows how to manipulate the parameters to reduce or basically minimize the loss function at every iteration. And so it's running multiple iterations right now, but it takes about and this is interesting how it shows seconds per iteration and iterations per second. But yeah, it takes about a second to run an iteration. And you can see that the value of the loss function is gradually reducing. And so here they've defined the tolerance for it, and when it roughly reaches that tolerance, it will basically stop and it will say, there you go, this is your solution. And it's an approximate solution, right? It's not going to give you the exact one. And it's specifically approximate solution to the problem of find me a unitary matrix, this matrix, that is actually of this form, that results in the value of the loss function being minimal. And that's what the unitary parameters will contain. And so this is running on the simulator right now, and I have a separate tab because I had to modify the example to run it on real hardware. But I wanted to show this because this actually works. The real hardware, I wasn't able to get it to work, and I will talk through that. It's interesting. And we're almost there on the solution. So once the solution is available, what they do next is they plot it, and in essence it allows them to compare. So they plot the approximate solution, and then they plot the analytical solution. And I want to talk about a little bit about the parameters. So here the example includes, obviously, because lambda and kappa in this equation, lambda and kappa, you have to for a numerical solution, you got to set them to some value, and so that's what they're doing. The other thing is that they do is the setting the boundary condition, and they're setting the grid because, like I said, you tabulate your data set, and then you kind of find solution in the grid, that follow the grid. So you can't possibly have values for all of the points. You can only have values for some of the points, and then you can interpolate the values if you need them for in-between points. Let's see. So the other interesting thing is the Fock dimension variable, and this will actually explode exponentially because as you increase the number of photons and the number of modes, and that also posed a problem for me when I tried to run it on real hardware. All right, so this should be finishing soon. All right, well, it's still taking a little bit of time. I'm going to show you the QPU example and the simulator. So I have created two programs that are in essence doing the same thing, but they're just doing it. One is doing it on a simulator, the other one is doing it on a quantum computer. It's the same circuit. So here, this is the circuit, and there's no difference. The only difference is in setup. On the simulator, I have to set a few other parameters that are not required on the real device. And when I ran them, so when I ran the simulator, I actually got the result. I got the sort of the probabilities, or in essence, the frequency. And when I ran it on QPU, I just on the real hardware, basically, I got an error, and I showed you the error right before, and it didn't make a lot of sense. So I couldn't figure out what was happening. So and this is the example from their website. So even the basic example didn't seem to work on their hardware. And this is interesting. This is still running, but it's getting very close to converging on a solution. All right. While this is going, I want to get into the actual QPU notebook, and it's basically the same stuff. All I had to do was change a few things here. Let's see. So the first thing that I had to do was when I set up the device. So initially, they use what's called a remote backend in their framework. I had to get away from doing that because you can't use that for running real hardware. Instead, I had to use a remote processor, and you have to feed in a token. Then and in fact, this backend, from what I understand, they don't meter that. So I was able to run this many times, and they didn't take any credits from me for doing that, which was interesting. But then you could do QPU or you can do simulator. So there's basically a couple ways to do simulators. One is metered, the other one seems to be basically free, which was also interesting to me. And this is probably because of the interface. This is remote. This is something they can meter. This one is running, from what I understand, in the same environment as the notebook. So they could probably meter the notebooks, but how are they going to do it? Per time that you spent in the notebook. Right now, this appears to be basically free. You can run this notebook all day long. All right. So finally, the simulated solution converged, and so these are basically the parameters for that circuit. Basically, this is the unitary matrix that represents that circuit, if you will, that solves the problem for us. And so then they plotted it, and so here you can see the blue line is the approximate solution, and the red line is the analytical solution. And this will vary. I ran it a few times, and like on different hardware also, and it seems to give different results. So like it's depending on the parameters, it might be closer or further away. And the loss function, to me, this one is not super important. I think data scientists and MLEs love to look at the the loss function just to get an understanding of, like, you know, how many epochs did it take, how quickly does it converge. But that's not super material to me right now. All right, so let me get into back into the real one, basically the QPU version of it. So here I had to use this remote processor API, and I wanted to show you on GitHub the API. So this is all open source. You can go and browse through their code base. And if you go to Percival folder, so they have a number of packages, but the ones that mattered to me were the backends. So the backends, there's this abstraction that they provide called a backend. It's an interesting actually way, a naming convention. Most of the time you don't see like a in front of a name, so that felt strange to me personally, but it must be some sort of a system that I'm not familiar with. And there wasn't a ton of documentation here, so it was hard to understand kind of what was the frame of reference or the thoughts in the mind of the developers when they built this. But all this implementation, so for example SLOS, this is a concrete implementation of that abstraction, and they have multiple layers. So a prob ampli backend, it's a bit shortened, which is making it even harder to understand. But and there's not a lot of like doc strings to really understand it. But this is just basically another flavor of a backend. And so you have all of these different backends, but from what I understand, they're all simulated when I looked at the documentation. So you can't run on real hardware with the backend abstraction. But then they have the, let's see, I believe this is under components. So they have this idea of an abstract processor. And so the remote processor, as far as I could see, it basically inherits from a processor. I'm not sure which specific file it's in. Yeah, I think it's well, it's not in the, yeah, okay, so you have processor, and then my guess is remote processor inherits from processor. But I didn't dig into the code too much, but to me, what I saw was that the API was different. So some of the functions that are available in the behaviors that are available on a backend weren't available on the processor. And so if I had to compare, right, let me go back to the computation function. I'm just gonna open it up like this. So you will see how this differs. So here in the original version, they're just doing backend set circuit. But with the remote simulator or remote processor, you also have set circuit, but then the way the output isn't the same, because here they can just take the output, and actually they get the output by running all prob is the method that they're running. But if you're doing a real processor, you have to call this sample count, and in essence that's the thing that basically forces it to run the circuit many times and get you the results. And so even though the name of the method is the same, the output is different. And let's see. So I wanted to run this just to show you what comes out. And this, hopefully this will explain like some of the challenges with the framework. And I felt like the framework was still in a state of being matured in terms of both availability, but also in terms of software that is provided to developers. And primarily, the reason for it is it wasn't very easy to interact with the system. It didn't seem like it was set up to intuitively perform some of these functions. And let me see why this is actually not running, or if it's actually running, because this was interesting. I didn't get the same behavior that I was expecting, but it looks like this is actually running now, which is fantastic because a few days before this wasn't working. But I think what may be happening, okay, I see what's happening. So the error actually is going to pop up from the minimize method. I was expecting it to pop up from the definition of computation function. So bear with me. It should pop up any moment now. So the other difference that I didn't talk about was so like I said, the way that you feed or get the results is different, but then you also, the way you compute. So here, for example, f of theta 1, you the way you compute it here is fairly easy. It's just one liner, but in the other example, so it's also one liner, but the reality is I had to perform multiple operations. So basically normalize the frequencies, so convert basically the raw frequencies into probabilities, right? And then I could feed it into the multiply operator. But anyway, so so this is still running, in fact, and I think that what might be happening is this is actually, this is not going to finish, and the reason is because right now the real hardware is not available. Let's take a look. So it looks like it's partial available, even though it's actually saying available, which is interesting. Maybe I need to look. So it's waiting. So right. So there's also a queue, so you have to wait. So I don't know how long it's gonna wait, but in the interest of progress, I'll just kind of skip that, and instead I will flip the simulator. And there's actually a way they give you sort of the queue size somewhere in here. I believe it's in the platforms section. I remember seeing it somewhere. I'm not sure where exactly you go. Total waiting jobs 15, right? So you get an idea of how long you need to wait. But I'm gonna flip it to simulator because it's not gonna make it a ton of difference. It's gonna be fairly similar outcome in both cases. All right, so this is the problem that occurs when we get the results. So you can see, like, I have 4 photons, and so those are the different states that I can get with 4 photons, or in essence 4 qubits, and the frequencies that were recorded during the sampling process. But then when I try to multiply these two matrices, because I'm expecting on the right side, I'm expecting all of the possible states, and on the left side I'm expecting only, or on the left side I'm also expecting, obviously the dimensions have to match up, but on the left side what I end up with is something that's shorter, right? The dimensions don't match between vectors, and so the vector on the left is only 15 and the vector on the right is 35, so you can't multiply them really. And so what you'd have to do is, and they have to be in a certain order, right? So if you look at them, there's some sort of order to them. So what the Quandela support person suggested is you just go through and basically substitute the missing states with zeros. And this should have been an easy exercise for me if I knew what the sort order was, but I don't, right? And so I was like, and sure, there's like what 20 missing ones, right? So I could theoretically run it on, like go back to some other example, run it on some simulator, get what the order should be, and just save them and basically kind of restore it from a file or something. But I think it's a bit of an overkill, and I actually tried it, but I didn't get any success. And what the support person told me was, well, you can just increase the sample size, and that would mean that some of the states that are missing will eventually get hits. And I tried that, and I actually didn't get a ton more hits, so it didn't seem to work. He said the number of samples had to be very large. But that also kind of defeats the purpose, right? Because the runtime will get outrageously long for this, and I wouldn't be able to do much of a demo. And so, without knowing what the order is, it's real hard to complete this program and substitute the missing states. And so I basically ended up dead in the water. I did reach out to the support person a few days ago and asked them, hey, what's the order of the states, right, in the results dictionary, and I didn't get anything, and in fact, now that I think about it, it's since it's a dictionary, it could be any order, right? So this multiplication, I don't know, there's something suspicious going. But my assumption there is actually an order to this. And I just don't know what it is. So and for me, again, like I need to figure out how to generate the missing states. So I never bothered to finish the example. And this basically concludes my presentation because I got into the state where it's just too much effort for me as a developer to figure out how to, in essence, work around the limitations of the platform. Because what I would expect was, or would be some sort of a parameter that says, hey, give me all the states for this specific problem so I can actually, feed it to some other algorithm. But that wasn't the case. It doesn't seem very easily configurable and doesn't seem to be very compatible with the examples that they give. So those are my sort of main learnings from this, is the framework and the platform. They're still maturing, but I think it's a great system. I absolutely loved support, and I absolutely loved the way everything is organized on their platform. I think the API has great potential to become sort of a leading standard, but it still needs a lot of work. And this is a recording, so I gave this talk in a meetup. There were some questions, like examples of questions that I got were, why do you think photonics might be hot, or basically why is there multiple organizations kind of chasing after this concepts and trying to develop it more? And to me, the main benefits are cost, because you in essence can run them in room temperature, so you don't need all the fancy equipment, and so that's one benefit. But also reliability, because the refrigerator units, I think that actually you have to maintain them, right? So it's not like 100% uptime that you could do. Although here we're not seeing a lot of uptime either, and so those were kind of good reasons. But another reason that I cited was that you can interface this with optics fiber communications, and then you have fully end-to-end photonic systems. You don't need a classical computer potentially. So that was another example that I cited. There were other questions asking, so like some of these variables, right, like the number of photons or the number of modes, you're basically doing hyperparameter tuning, trying to figure out what's the optimal, number of photons or modes for solving your problem in terms of both speed, availability, and sort of the quality of the solution, or basically accuracy. And they were asking, well, are there any frameworks to solve this problem? And I said, I'm not aware of any, and the main reason is that I think that, and I said, I don't believe it's a solved problem. There might be something that is out there that's aiming to solve it, but I don't believe that it's a solved problem, because if it was something that was easily solvable or like well understood problem, I think Quandela would actually leverage that, but I don't see them doing it. Maybe it's just, again, they're still maturing it, but I don't recall seeing similar systems in Qiskit a few years back when I tried it, and so I didn't see it in Ocean as well. And so I don't believe that's a well solved problem. When I looked at Penny Lake or Penny Lane from Xanadu, it seems like they claim that they solve it and they have everything figured out. But I would think that the competitors would also catch on to this and try the same kind of an approach. So, but I've not had time to really research what Xanadu does with their framework. So yeah, so this is the presentation in essence. I hope you enjoyed it. I hope this was interesting for you to watch and listen to. One more thing though, there was one more question. The question was, so, you talked about all these different frameworks. Do you have any way to basically benchmark and compare them? And I said that yes, there's this idea of quantum volume, and we can, in essence, build a circuit that then can be run on different hardware, and we can then compare how different systems, perform compared to each other. And this has been an idea of mine that I wish I had the time or resources to implement, but I'm sure some other company or organization will build that. I see that the benchmarking concept comes up regularly, and I think it won't be long before somebody builds a benchmark that runs across all the different quantum hardware that is available currently. So I believe those were mainly the questions. So again, thank you everyone for watching this, and I hope to bring more content like this in the future. So thank you again, and goodbye.